This is a recording for the expert to novice presentation for COM217. Hello, my name is Suhani Sundar and I'm a senior at Purdue University studying physics. I do research in the field of atomic, molecular, and optical physics, and that has a lot of quantum mechanics, which is related to the topic that we're talking about today. So the topic that I'm going to be talking about today is Schrödinger's cat, did it actually happen? The 3 points that I'm going to be talking about is Schrödinger's cat, is the fact that Schrödinger's cat is a thought experiment, superposition only happens at the quantum level, and measurement and interpretation are different in quantum mechanics. So what exactly is the Schrödinger's cat thought experiment? And I would like to first define what a thought experiment is. And it is as it sounds. It is an imaginative experience that an imaginative experiment that a person would make in order to hypothesize something. And in this case, Erwin Schrödinger thought of this in 1935 to try and explain how complicated and confusing quantum mechanics is. As you can see in this picture, the thought experiment that he thought of was that he would place a cat in a box with a radioactive atom, a Geiger counter, a vial of poison, and close the box. And the idea is that if the atom decays, it would trigger the vial of poison and the cat would be killed. On the other hand, what could happen is that the atom does not decay, the vial is not triggered, and the cat is alive. And the cat and the radioactive atom are both in a state of superposition, and we don't really know what is going to happen until we take the lid off the box. So why did he think of this? It is to show how complicated it is. And this is a quote that he himself said, and he wrote this in his own paper in 1935, which says, "It is typical of these cases that an indeterminacy originally restricted to the atomic domain becomes transformed into macroscopic indeterminacy." And this basically states that this basically states that if something seems to be unclear and fuzzy in the quantum level, it's very likely that it's going to be unclear and fuzzy at the macroscopic level. So why is it that we cannot see this phenomenon in real life in things that we actually see? And the answer for that is superposition. Superposition is a phenomenon where an object is in two states at the same time. And by objects, what I really mean is a particle, such as an electron or an atom. If we take an electron for an example, it can be in two different states, an up state and a down state, and it will be in those two states until we observe it, in which case, once we do, the result is going to be either it's going to be in the up state or a down state. And this is the reason why we cannot see it in the macroscopic level. It is a phenomenon called decoherence. And decoherence is essentially where you have multiple, like millions and trillions of particles, and they essentially cancel out. And in the case of macroscopic objects and beings like cats and people, because we have so many particles in our body, it's not really feasible for superposition to take place, and hence decoherence takes place, and all those effects are cancelled out, and we cannot see it in real life. So what actually happens when we make a measurement? And this is actually a quote said by Niels Bohr, who is one of the founding physicists of quantum mechanics. And he essentially says no phenomenon is a phenomenon until it is an observed phenomenon. And one of the most popular interpretations that we have for measurement is something called a Copenhagen interpretation, which essentially states that when an object is measured in quantum mechanics, it collapses into one single state. As we can see in this image, if we think of superposition happening in a particle as a curve, as a bell curve, when we measure it, it turns into this spike, and the distribution that we had over here is gone. And one of the most famous experiments that we have to illustrate this is the double slit experiment, where we have an electron and we place it in front of a double slit. When it is not measured, the electron behaves like a wave. It goes through both those slits, which would not be possible for a particle. And then it creates this interference pattern that we can see here. But when it is measured, it goes back to behaving like a particle, which we now call the wave-particle duality. So essentially, this electron that we have here acts both as a wave and a particle, which outside of quantum mechanics, it's very, very unusual that this happens. And this is another quote by the physicist Richard Feynman, which highlights how complex quantum mechanics really is, which says, in reality, it contains the only mystery. Another interpretation that we have for measurement in quantum mechanics is called the many worlds interpretation. And this interpretation essentially states that you don't really have a measurement collapse per se. However, all those different scenarios that you have, or the different measurements that it could collapse into, all happen in a different parallel universe. And an MIT physicist who works on this says, in the many worlds interpretation, everything that can happen does happen in a parallel universe. And whilst quantum mechanics is a growing field right now, and it has huge applications, going into quantum computing and everything, when it was initially formed, when the theory was initially formed back in the 1930s by renowned physicists like Erwin Schrödinger, Niels Bohr, Heisenberg, etc., there were a lot of physicists who just thought that it wouldn't be possible, and one such physicist is Albert Einstein, and he thought that quantum mechanics it does not make sense, and it cannot be possible. And he says, God does not play dice with the universe. So in conclusion, this presentation, it was made to highlight how complicated quantum mechanics is and how far we have come. And we can see this through the phenomenon of superposition and decoherence, which illustrates how it works in the quantum level and how it cannot work in the macroscopic level, and how measurement works in quantum mechanics. Whilst I did mention the many worlds interpretation, it is not what is commonly used in experiments today. The ones that are used in the experiments today is the Copenhagen interpretation. And yeah, thank you so much.